to go over a few housekeeping issues. You have joined this webinar in listen-only mode. You will be able to hear the presenters, but due to our size today, we won't be able to open up the microphones to hear you. However, that doesn't mean you cannot participate. We will be offering several chances to interact with questioning. If you look on the right side of your screen, you will see a questions area. If you'd like us to answer a question, please type it in here, and we'll collect all questions to answer at the end. We will also use this feature a couple times throughout the webinar to share your thoughts on some discussion topics. For those of you interested in receiving continuing education credits, we can offer evidence of attendance for those participants who stay with us through the duration of the webinar and take the survey, which will be sent to you through an email after this webinar. The proof of participation will also be sent through email. I'd like to introduce Julie Olson. Julie Olson has been teaching high school science for 24 years. She is an adjunct professor of biology for Dakota Wesleyan University, as well as Northern State University. Mrs. Olson is a current Society for Science and the Public Fellow, South Dakota Outstanding Biology Teacher Award Rotary Teacher, and 2007 Presidential Awardee for Excellence in Science Teaching. Mrs. Olson is very involved in science throughout the state with participation in initiatives such as curriculum development for Science on the Move, a mobile science lab, and the James Project, a statewide water quality project. She currently serves as the co-chair for the NCA, North Central Accreditation Review for her school, as well as Science Department Chair, Principals Leadership Team, Principals Cabinet, and the Science Curriculum Review Chair. She lives in Mitchell, South Dakota with her husband Mel and 2 college-age children. Julie, we're so glad to have you here with us. Let's get started with the presentation.
Okay, well, welcome to everybody to Engineering Design in the Life Sciences. We have a couple of goals for today's webinar. We want to be able to differentiate between engineering, science, and technology, locate the engineering core ideas and practices within the NGSS, and learn how to engage students in engineering activities utilizing practices, cross-cutting concepts, all integrated with disciplinary core ideas. So let's get started with the polling question. Let's see if you know what engineers do. So you have the polling, and so you can select your answer, solve problems, answer questions, build things, or design. Okay, looks like we have a pretty split decision on here, but let's discuss the choices. I think the general public would probably choose C a lot of the time. At least that's what I would have probably chosen when I was in high school, build things, because I guess that's what I always thought engineers did when I was a high school student. I can only imagine the possibilities had I known about things like bioengineering. D, design, is pretty broad. With what respects are we talking about? There are graphic designers, interior designers, you get the point. B, answer questions, is actually what scientists do, and that leaves only A, solve problems. They use science, and vice versa, science uses engineering. Take, for instance, the evolution of the microscope. As new devices are engineered, the questions that can be answered, the discoveries that can be made, increase. So let's look at science, engineering, and technology. And you notice how this is a pretty good representation because they do interact and affect each other. engineering is the practice of design to solve human problems. And so we're looking at things like identify the problem, or asking questions if you're talking about science. And this is where we want to go. We want to look at what is some of the differences between science, engineering, and technology. You can see how identifying problems to solve requires questions to be asked and investigated. A new term used in the classroom for a lot of teachers is going to be the concept of constraints. To simplify this, these are basically like the rules of a game. And so we're talking about values like aesthetics. What does something look like? Economics, the money factor, social, and moral values. So that's what we're talking about, constraints. What limits are there? What are the trade-offs? What are we willing to sacrifice? What do we want to gain? What is the minimum that we will accept? There will be competing designs, so there will be argumentation. Which is best? Is it good enough? Can it be made better? I challenge you to challenge your students when engaging in engineering to ask themselves, how can I make this better? Where would we be if Leeuwenhoek's first compound microscope was good enough? Science, again, answering a question. There may not be an immediate need, curiosity-driven, and these would be our traditional disciplinary cores. But again, that's the idea with the NGSS, is to bring in engineering so the students have to utilize that information. Technology. Technology is basically defined as human-made systems, and it can be processes too, often the result of engineering. It can be a collection of tools to do a task, that system, and you're going to hear about systems a lot with NGSS. And so the big thing here, at least something that I struggle with administration, is what is the definition of technology? Most of the time people will automatically think of computers, but it can be so much more. It can be sensors. It can be various data collection devices like electrophoresis equipment. It can be a set of specific processes that have been engineered, like staining blood cells, for instance. And so then we get to engineering design. It's not really a linear process. I know there's these three listed here, but it's more cyclic. Again, we see that with the scientific process too. It always leads to more questions. We always have to be looking for something better. It might be that we have to engineer a new tool to go beyond. But again, with engineering, defining and delimiting engineering problems, designing solutions to engineering problems, and then that optimizing. Again, how can we make it better? So the engineering practices, some more of those. We have defined the problems. Now these correlate with the science practices. Again, in the NGSS they have science and engineering practices. So in engineering we have defining problems. What is needed? What is desired? What needs to be improved? Examples, do we need it smaller? Do we need it faster? Do we need it stronger? Developing and using models. Models must explain, be used to predict, and test. Can it be an animal model, such as fruit flies, or plants, such as lettuce seeds used to test a newly engineered drug's effects, or a product, or a new plastic? Both good and bad. You know, we could test for good things. We can test to see if there's adverse effects. It can also be mathematical, such as an equation. They talk about algorithms, computer programs to predict future earthquakes, population models. Again, we get to that where models can be simulations. We can't all afford all the types of materials for the classroom or build things like a large roller coaster or an entire ecosystem. And you will find these on such resources as PhET. That's a capital P, little h, capital E, capital T. And one of the ones that comes to mind is a simulation for global warming. There are simulations that are numerous that do a good job, but we should always ask, are they adequate? How accurate are they to real life? And I think that's an important question to ask your students when you have them do a simulation. I'm not against them, but also bring in that discussion. How accurate do you think this is? Is this really a good model? Some more of the engineering practices. Data in itself is not enough. Just seeing it is not enough. There must be an analysis, be it a pattern, a mathematical equation such as slope, statistics, construction of graphs. Once it is analyzed, what will that analysis be used for? Proof of the best, constraints, met, cost, all those. So when you ask students which design was the best, what's your proof? What's your evidence? Designing solutions, seems like we just talked about this one, but those are the steps that comprise this practice. This would be the students taking the reins and designing the solutions. For the others before this, they may be presented data and asked to evaluate it. They may be given mathematical equations or graphs related to testing. An example might be that they were given biodiversity data for a new man-made pond. Did they design the pond correctly? Having them actually analyze that. We have two more practices. On number 7, the key to number 7 is it evidence-based? Not, as a statement would be that it's what it used to be, so it must be okay. You need to, again, ask for that evidence. Communicating information is important for both scientists and engineers. The form of communications can vary depending on these skills, materials present, and goals. And you'll find that this is a very natural lead-in to the Common Core standards. Where do you find the engineering performance expectations? Well, there are a couple of places. Within the performance expectations, that's the PEs, those are the ones at the very top box when you look at the NGSS, and there will be an asterisk after those. And then if you look down into the foundation boxes, those are the 3 boxes below, then you will see engineering. There also are separate, broader engineering performance expectations that could be applied to literally any of the areas of science. So let's start looking at an example. This is from the middle school life science engineering, and so it does have an asterisk. And so here's an example of what could be done to instruct the students. With this one, students don't need to actually design solutions. It's asking them to evaluate competing designs. And so an example could be different methods that have been used to reestablish reefs. There could be data there, pictures, reports on, they've used scaffolding, they've sunk ships, they've sunk planes. I just seen an article where they're actually learning how to cultivate different corals. So you could present them with that information and then they debate which method is the best. I like to go with a hands-on approach, so I'm going to go take this through from the beginning of the whole instructional sequence. So the first part is engage the students. What if their example would be, what if there's only one kind of potato or banana or no clean water or only one kind of fish? So taking the banana, Did you know that they were in danger of becoming extinct from markets due to some disease that was attacking them? And now they have since figured that out, but you know, you could do history, you know, the Irish potato famine. Local problems build buy-in from the students. You gotta catch their attention. Presenting their plans to the local city council or school board could be a way that they could actually, you know, present and share that information. Models for abstract ideas, you can provide various bags of colored beads that might represent different ecosystems. And that ecosystem with low biodiversity might have 1 or 2 colors of beads. And then one might have a whole bunch of colors of beads, or you can use candies or whatever. But again, when you're using models, a really, really good question to ask the students is, how is this a good model? Could it be better? So I think that one's going to get a lot of discussion. The next steps, picking a local, state, or global biodiversity problem. Water quality is one that I think a lot of students can relate to. Research methods for remediation. Keep in mind costs, benefits, drawbacks. These are those constraints. So, as some ideas, each student or group could pick their own problem. If you don't feel comfortable with that, you could assign them all one kind of problem. Let's vote as a class. Which one are we most concerned with, and go with that. They need to learn how to look for and assess information. Research what has been done locally and elsewhere. What are the probable causes? What are the good and bad about current methods of remediation? What are the constraints for trying to solve the problem? Again, cost, materials, location, even societal constraints. You know, if we're talking about water, such as the Ganges River, is severely polluted. But again, we have a very strong societal and religious connection to that, or the people in the area. Then, what's going to be an acceptable level of remediation? And then, how clean does water have to be? So you can see where these are really going to draw in a lot of the science skills. They're going to have to use a lot of knowledge to explain themselves. So how would you actually carry this out? And one of the big concerns is the cost. As writers, one of our goals was to not write something that was going to be cost prohibitive. So an example, give the students a whole pile of different things. So empty plastic bottles, again, recycled. It could be metal cans, a bucket of dirt, a bucket of sand, cotton balls, old cloth. Just very simple things. So hopefully that gives you an idea. Let's look at another one. Here's maybe a little more focused. There used to be abundant honeybees, steady decline. They call this colony collapse disorder. There's been links to other, and so we've got this biodiversity. You have connections and interdependence of organisms on each other. You're going to find that you may be able to bundle performance expectations. This would obviously be one of those. So some background information. These neonicotinoids are nicotine-like insecticides that are toxic to invertebrates. They have been engineered to be water-soluble. Again, engineered, so we're going to assess a problem caused by an engineered substance. Can be put on soil and taken up by the plants themselves. They kill sap-feeding insects as well as cockroaches and flies. We can all see their benefits. What are the downsides? What is the problem? What are some other insecticides? Or do we know a non-lethal way to control them? At the high school level, students could try to use soaps, other plants that have been rumored to deter insects such as citronella or marigolds, on fruit flies, again using a model organism. And then students could even debate that. Are fruit flies, I would suggest flightless, are they a good model to show what might happen to honeybees? Another one. Now this one's a little bit different from the middle school, and I think that's a really important thing to point out. At the high school level, when people first read it, they almost look the same. But in this one, the students actually design, evaluate, and refine a solution or a proposed solution for reducing the impact of human activity on the environment and biodiversity. So giving you some ideas, and that's the nice thing about NGSS is they do give you a lot of leeway. So you can build in, you know, things that are important to the students from a particular area. So examples, fishing. You could bring in hunting, building development within a city, deforestation, non-native species, endangered species, oil spills if you live by a coastal area, selective breeding, dogs, crops, and then the human activities, how they affect the environment. And so you can have some really good brainstorming sessions. One of the things as a teacher you will have to, if you don't already, is to give up a little bit of the control. You've probably heard the guide on the side, not the sage on the stage. And so each team investigates their own ideas, so you get that collaborative work that's so important in the scientific and engineering world. And again, some of this is going to depend on what resources do you have available. Using models, we talked a little bit about this, but it can be a simulation. It can be a mathematical equation to predict population growth. It could be a graph looking for patterns between, say, predators and prey. Some other simulations, I know online if you Google peppered moth simulations, again there's the PhET simulations, they have global warming. The Nobel Prize Association has a blood transfusion game. So those are some models that they can use. Using mathematical and computational thinking, is there current data? What trends and patterns? Again, the patterns, that is a cross-cutting concept. Can these be created or can you find those? Population growth and decline. World population is out there. They have an online world population counter. How true do they think that is? Can they use it to predict? Designing solutions, obtaining, evaluating, and communicating information. What is being done? What are the constraints? What's the good and the bad? Those are important. Can they model this electronically or on paper? Can they draw it? Can they actually build a model? Again, the water purification example, that is a model. Could it be scaled up? Again, there's that concept of scale that you will see in the NGSS. And then engaging in argument from evidence. So again, going back to the water purification, if each team has their own idea, okay, whose is the best? What's your criteria for determining that? Even from the winner, is that good enough? Would they drink it? If you're talking about in the Midwest, where I'm from, hunting and fishing is big. Well, if we set certain rules, okay, well, is that going to give us the ongoing sustainable population that we want of whatever we're hunting or fishing? And there's a lot of ways that students can do this. Posters, just an oral presentation, PowerPoints, Prezi, a good debate between the students. So let's have another poll. What are teachers going to need to enable students to engage in engineering standards? Okay, so let's talk about those. Change is not going to come quickly, but you'll be surprised at how fast the students come to recognize the engineering practices and cross-cutting concepts. Again, I would recommend having a poster, or even have the students assign them one of the practices or one of the cross-cutting concepts and create a poster to put up in the room as a visual reminder. I'm constantly reminded to point those out to the students as they are engaged in science and engineering. It breeds familiarity. It then leads to connections and then starting to ask themselves the same things. So yes, it's going to take time. It's going to take resources, be it materials for the classroom, even simple things like a bucket of dirt or a bucket of sand or collecting plastic bottles. You know, we're already strapped for time. Money will help, but again, the NGSS were not written to be cost prohibitive. There's lots of simulations, but again, that depends if the school has the adequate technology. So I would pick all three, but again, I do believe it does depend on the situation too. There are a lot of resources out there. If you Google engineering for high school, there will be a lot of resources that will come up. So let's look at one more that I found really interesting. It is one that is in the McGraw-Hill curriculum. And this activity brings forth what we call anthropogenic or man-made effects on ecosystems that are being found to disrupt ecosystem stability, which is cause and effect. And so microbeads, if you go and look at body washes, hand soaps, they'll say that they exfoliate. And so a lot of those have microbeads. Some have other things, and that's something that, you know, give the students that answer right away. Have them, you know, do some research. You'll be amazed at what they come back with. But what they're finding is that these microbeads are persisting in aquatic environments. They actually, being plastics, are soaking up pollutants and being consumed by wild organisms. So we also have biomagnification happening. It is not able to get filtered out through wastewater treatment plants. And so there's obviously a problem to be solved. So defining the problem, going through that series of steps. The problem is to remove the microbeads. or maybe not. You know, obviously they're already there. Some students are going to say, well, can we not even put them in there? Are there other alternatives? What's the level of harm actually out there? Is it worth the cost to remove them? So the economics. This is only one type of water pollution. You also could bring in fertilizers. They're finding that pharmaceuticals, even aspirin, Tamiflu, there's pesticides in the water. So you could gear it towards other things. Clean water, what are the benefits that clean water provides? Ecosystem services, you could ask them. So drinking water, recreation, water for crops, cooling, you know, producing food, maintaining biodiversity. So terms, you could get in terminology here, the vocabulary. Again, we're looking at connections to the Common Core. So you can see biodiversity, trophic interaction, or feeding levels, bioaccumulation, biomagnification. Going back to the NGSS, where would this fit in? So we're looking at life science. We've got the ecosystem dynamics, functioning, and resilience. We have biodiversity and humans. What's the human effects? We also have the engineering. What's the influence of science, engineering, and technology on society and the natural world? Again, so we're seeing all these, as you may have heard me say, bundling things together. So here is an actual engineering performance expectation. Evaluate a solution to a complex real-world problem based on prioritized criteria. Those are those constraints. What are your rules for an acceptable solution? Also pointing out the trade-offs, the bad, what are you giving up? And so, again, cost, safety, reliability, aesthetics. Is it going to look okay? That's what aesthetics is. Your social, cultural, and environmental impacts. And again, here is some of those constraints listed again. And it might not be, like I said, do you actually want them to build, or do you want them to propose possible solutions? Could they draw a model or a possible solution just on paper? And then maybe those students that always seem to finish first and have everything done, well, some materials, do you want to try to build something, or even trying to get the microbeads out of some hand wash to actually look at? So there's a lot of avenues, again, trying to address learners of all levels. The project design, again, asking those guiding questions. Again, this is kind of following the evaluate and redesign process of engineering. Again, based on the results of their analysis, make modifications or even just propose modifications. Depends on how far you want to carry it. What's your time limits? What's your material limits? And then the argumentation. Okay, if you have several groups and students doing this, what's the best design? Okay, so let's have one more poll. When or should science and engineering practices be used together? Always, never, or it depends on the activity? Okay, so we're pretty much, we have some that always. Sometimes, ideally you would use science practices and engineering practices quite often with each other. Again, depends on the activity. Again, it's also going to depend on your time, what materials you have, and what are your instructional goals. So it actually, I would pick C, but I could see with A that, that's going to probably put a lot of stress on a teacher. But it's pretty easy to use some of those. Once you get used to them, it does take time. So we'll open up for questions.
At this time, Julie, there's no questions in the queue at the present time, but please be aware that you can enter a question or comment in the questions area in your go-to. All right. Well, thank you for attending this webinar. A survey will pop up at the end of this webinar. We are so grateful for your feedback so we can improve the experience for future webinars. You will receive a follow-up email containing a recording of today's session and evidence of your participation, which you may use towards continuing education units or CEUs. If you have any additional questions, please feel free to email webinars@mheducation.com. You can learn more about the next generation standards at mheonline.com/NGSS. Thanks for attending this webinar with us, and have a great evening, everyone.